Good morning, good evening and good night. Welcome to this lecture number 4 on the solution chapter. In this chapter, so far what we have discussed, let us have some recap on that. In the first lecture that we have discussed about the very solutions, that is the definitions of the solutions, and we have also discussed regarding the what is solute, what is solvent, and the different types of solutions. That solution can be of the 3 types, but in the 3 types you will find that they will also, when we change the solute, this can be have the other sub classifications that we have discussed in details with the examples. Also we have discussed how we are able to describe the concentration of a solution. That can be described in the different ways, that also we have discussed in that lecture number 1. Then in the lecture number 2 we have discussed about some important relationships, that is relationship with the mole fractions and the molarity, mole fraction with the molarity, and the relationship between the molarity and molarity, that we have also discussed, and we will also discuss some one numerical also, which type of numericals is going to come, that is also we have discussed. In the 3rd lecture we have discussed about the solubility of solid solvent, and there are basically different factors which are going to influence that solubility of the solute in the solution, that is we have also discussed. In this lecture we are going to discuss, this will be the 4th lecture, we are going to discuss another, that is that we will discuss the liquid solutions. But with the liquid solutions, in this liquid solution there is the solute is gas. So heading of today's lecture is the solubility of the gas solute in the liquid solvent. So we can write the today's heading of this lecture, solubility gas in liquid. First, let us understand how do we define the solubility of gas in liquid. Solubility of gas is the volume So solubility of gas is the volume in milliliter that has been converted into the STP, standard temperature and pressure, in a unit volume of solvent to form a saturated solutions at the temperature in which we are carrying out this experiment and within the 1 atmospheric pressure. So this is the definition of the solubility. Now we are going to discuss what are the factors that are going to influence the solubility of the gas in the solution. So now we will discuss the factors. Factor number 1, that is the nature of the gas. Nature of gas and solvent. Like oxygen, hydrogen and nitrogen. is found very little solubility. Little solubility. Whereas you can see, we can write this, that whereas HCl gas, H2S gas, NH3 gas, all these are very highly soluble in, it is a gas and it is highly soluble in water. This oxygen, hydrogen and nitrogen is found very little solubility in water, whereas in case of this HCl gas, H2A gas, NH3 gas, it have the very significant solubility in the water. Why it is so? It is because of the similarity in the chemical structure. H2O and HCl gas, H2S gas, NH3 gas have the similar chemical structure, that is both having the dipole moments. That is why this can easily be dissolved in the water. Okay, that is very simple thing. Second, that we are going to discuss the pressure. Pressure, if we increase the pressure of the gas above the solution or above the liquid, the solubility of the gas in the liquid is going to be increases. So we can write, so if we increase the pressure has been increased, pressure of the gas has been increased, and the solubility also goes on increasing. This can be easily be understood by taking a system like this. This is a system. In this system you can see there is a two phase. One phase in the bottom of this container you will find there is a liquid. This is a liquid, right? And in the upper, this here has the gas phase. Gas phase at pressure P and temperature T. This is a gas phase and this is the liquid, and it's gas having the pressure P and temperature T, and there is a dynamic equilibrium between the liquid phase and the gas phase. That means the number of gas particle leaving and going into the solution phase is same. Now what we are going to do, we will do some experiment. We are changing the volume of this gas. We are changing the volume of the gas. It is previously the weight portion. We are pressing the gas. By reducing the volume, we are increasing the pressure on the gas, and that is been doing by making some weighting arrangement. We are compressing this gas. So what is happening here? You can see the volume portion, the volume of the gas. Now you can see previously this volume of the gas is this. This volume is this. Now this volume of the gas you will find above the solution. It is this. This is the solution phase and this is the gas phase. Now when we increase the pressure of the gas by reducing the volume, what is going to happen? Number of particles per cc, per unit volume, now it has been increased. Previously it was lesser. Now it has been increased, and this means the number of particles that is going into the solution, or you can say striking the solution or liquid goes on increasing, and that is why you can see that solubility, that is the amount of the substance, amount of the gas is going to the solution, has also increased. So we can easily understand, when we increase the pressure on the gas, the solubility of the gas in the liquid has been increased. Okay, and this is quantified by one scientist, one chemist, that is, his name is Henry. Henry was able to explain this phenomena quantitatively, and this is called the Henry's law. This is called Henry's law. What this law says, let us understand. It says the solubility, you can write this, what Henry states. Henry states that solubility of the gas in the liquid, solubility of the gas, that is the mass of the gas in a given volume of the liquid at a particular temperature, is directly proportional to the pressure of the gas above the solution. Means this pressure, when we increase this pressure, the solubility is going on increasing, and he equate this with a proportionality, that is mass of the gas, that is mass of the gas is directly proportional to the P. You can see that from the Henry's law, we can see the mass is directly proportional to the pressure of the gas. So we can write this M is equal to KH into P. P is the pressure of the gas. Here KH is called the Henry's constant, Henry law constant, Henry law constant. This is Henry law constant. Suppose there is a mixture of gases, then what is going to happen? And this mixture of gases is in equilibrium with the liquid. So at that time, we can modify this Henry's law, that we can say that here also, here the solubility, we are talking about the mass. Then at that time, when it is a gas, we can consider, we can describe the solubility of gas from the mole fraction. So we can write this equation further, the solubility of the gas, solubility of gas represented by the mole fractions, mole fraction of gas in the liquid is directly proportional, directly proportional to the partial pressure of that gas, to the partial pressure of that partial pressure. Partial pressure of that gas.
Suppose there is a mixture of gas. In that gas mixture, you want to know this gas, amount of this gas, how much it is in the solution. At that time, the solution solubility will be represented by the mole fraction of the gas, and if partial pressure will be responsible, partial pressure of this gas E above the solution will be responsible for the solubility in terms of mole fraction. So we can write this. Suppose mole fraction is XA and partial pressure of the gas is PA, so it will be this. So we can further write XA is equal to KH into PA, and here KH, that is the units of KH, you can see that is atmosphere inverse, or you can say bar inverse. But this equation normally been written, more popularly written as like this: PA is equal to KH into XA. At that time, the units of KH will be different, atmosphere and it is bar, atmosphere or bar. So this is the equation, Henry's equation, that is the mole fraction in the gas is directly proportional to the partial pressure of the gas above the solution. And if we make a curve with this partial pressure and this mole fraction, what we will find? We will find this type of curve. In the x-axis, we are plotting mole fraction. In the y-axis, we are plotting the partial pressure. So what we will find? We will find that this curve is like this. It is a straight line. This is a straight line passing through 0, passing through the origin, and the slope of this curve is KH, means Henry's constant. So this is a straight line which have the slope is equal to the Henry's KH, that is Henry's constant. Henry's constant, hence the law constant. This is Henry's constant, or you can say Henry's law constant. And from this you can have some conclusions that we are going to understand how pressure of the gas going to influence the solubility of gas in the liquid. And from the Henry's law we are able to understand that it is the increasing the pressure that will going to increase the solubility of the gas in the liquid. And how it is so? By way of mole fraction in the gas, we can able to say the solubility of the gas in the solution. So we have make a curve, we have make a graph of this, that is Henry's constant. We will find that it is a straight line. When we plot a curve with the mole fraction in the x-axis, in the y-axis is the partial pressure of the gas, we will find this will be have a straight line. Now we can conclude 2-3 very important things. Number one, this KH is the function of the gas. This KH is function of gas, means this value is depend on the gas. It is not a fixed one, that depends on the gas. So you write KH is the function of gas. Number one. Number two, KH, if the pressure, if the KH is high, if the KH have greater value, have higher value, means the solubility of the gas is less. You can easily understand this. Solubility of gas is less. How do we do that? Suppose this is the solubility, means that that is represented by the KH, and this KH is a constant. if this kH is higher, means the solubility will be lower at the same pressure. That you can easily understand. Suppose this is the kH means its slope of the curve. So at that point you will find the solubility of this is this amount. When the slope has increased, some other gas having the defined kH and it is found its kH value is higher. If the kH value is higher, means Henry constant is higher, at this time the slope will be higher. So with the same pressure, suppose this is the pressure, in the same pressure you will find its solubility will be less. This solubility is corresponding to this curve and this solubility corresponding to this curve. So higher the kH value means higher, lesser will be the solubility of the gas. That is why, right, if the kH is have the higher value, means the solubility of the gas is less. And another thing, the value of the kH depends on temperature. Means if the temperature is high, then kH value will be high. That we can easily understood from this data. You can able to understand how the kH value depends on temperature. You can see oxygen have the kH value, Henry's constant. This is Henry's constant. kH value, or you can say Henry's constant. That is, you can see at 298 Kelvin, it is having the 334.86 kilobar. Whereas when you increase the temperature to 303 Kelvin, it has been increased 46.82. In the nitrogen also you see 76.48, and now when you increase this temperature 303 Kelvin, it will be 88.84 kilobar. So with the temperature, from this we can able to understand the solubility of the gas is going to reduces. That we are going to. As we have already discussed in our previous lecture regarding the solute, and it has a different trend. It depends on the enthalpy change of the reaction. If the enthalpy change is exothermic, at that time the impact will be negative. When enthalpy change is positive, that is endothermic, at that time the temperature change on the solubility will be positive. That we have already discussed. Here we will discuss these things. First we have to understand this process of dissolution of the gas. That gas has been dissolved in the gas. What about this process, whether it is the exothermic or endothermic? For that we have to understand about is enthalpy change, then whether it is positive or negative, that we have to understand. And from that we will be able to understand with the increase of the temperature whether the solubility will increase or decrease. So we know from the thermodynamics chapter, that is delta G, that gives free energy change, it is delta H plus T into delta S. That we know from our thermodynamics chapter, that there is a relation between the free energy change with this entropy and this enthalpy and the temperature. As the dissolution at the this gaseous material, gas has been dissolved to the liquid, it is a spontaneous process. So we can say del H is negative. And what about the entropy change? As the gas has been dissolved in the liquid, at the time there is no specific arrangement of the gaseous particle in the liquid. So we can say entropy change is also will be negative. So on this, if it is negative and delta is also negative, then naturally you can able to say delta H also will be negative. means the process of dissolution of the gas, process of going the gas into the solution will be, you can write this solute gas plus solvent liquid, that is solution. Solution means that is liquid solution. Okay, so we already understand this is also there is a equilibrium, dynamic equilibrium is achieved. This is in the both ways, that solute gas will go into solution and some solute particles, gas solute particles in the solution, that will be coming back to the atmospheric atmosphere. At that time this will be the reaction, and in that reaction this will be the forward reaction, and in that forward reaction we can see there is a evolvement of the heat is evolved. So when we apply the Le-Chatelier's principle, when we apply, at that time we can easily understand that when we increase the temperature, the reverse reaction will goes on, means the solubility of the gas in the liquid solution will certainly going to be decreases. As we increase the temperature, the solubility of the gas will be decreases, because it is a exothermic process. Okay, so temperature means higher temperature. So we can write increasing temperature, we can write this increasing temperature shall decrease the solubility. Decrease the solubility. Further, we can able to assess how much quantity has been dissolved in the solution. Gas has been dissolved in the solution. That can be also we can able to understand by this equation. This equation is like the Van 't Hoff's equation that we have already discussed in the equilibrium chapter. Here C2 and C1 is the solubility, or you can say the concentration. Solubility at temperature T2 at temperature T2 and at temperature T1, and delta H is equal to enthalpy change and R is the universal gas constant. So we understand how the gas solute is going to be soluble, going to dissolve in the liquid solvent, and what are the factors which is going to influence this, that we have understand clearly. If you have any doubts, you can comment in the comment section. So that is all for today's lecture. The next lecture we will discuss the next thing, that is the liquid in liquid solution. At that time we will understand about the vapor pressure, how the vapor pressure going to influence, and that is the Raoult's law, and that will be discussed in next lecture. That is all for today's lecture. Thank you very much.